Okay, we're doing streaming today. So what's the idea here is streaming. Maybe afterwards you can go back and see why I'm doing this, right? You see the whole thing, and now you only see a little bit of it at a time. That's sort of the idea. Okay, so there's this paradigm both in the last lecture and in this lecture that we're doing. It's a little bit more from probability and statistics, some combination of probability and statistics and algorithms, and using those ideas to compute things, essentially, or calculate things. So, for example, last time we did similarity, we were talking about the similarity of two documents, and we had this notion of similarity, which is this, the number of words in their intersection divided by the words in their union. How many words do they have in common as a fraction of the total words? So we wanted a fingerprint so that some function of the fingerprints, and the fingerprint, what's a fingerprint? A fingerprint is a fingerprint, right? So it's not you, it's just something about you, right? It's not the whole, all of you, it's just a little bitty thing that with that we can identify you, right? That's the idea. Okay, that's what a fingerprint is. Here, we want to use these fingerprints in a little bit more complicated way, not just to identify you, but for example, that's a hash. You might think somebody's MD5 hash is a fingerprint, right? If you take a big file, you take their MD5 hash, and that you pretty much maybe uniquely determines the file. Okay, even though it's much less in size than the file. Now, so there's nice fingerprinting techniques that you've seen, maybe, if you know what an MD5 hash is. Who knows what an MD5 hash is? Okay, it's just when you get a file, you take all the words and you hash it into one string of some 248 characters or 512 characters, and that block is there's not so many files in the world, so by the birthday paradox you expect those things to be unique, right? There's only a gazillion files, whatever number that is, and that's less than 2 to the 512. So you expect this hashing to be unique, so that fingerprint uniquely tells you what the file is. Here we want something a little more clever. We want to say for two files we write a fingerprint for one and a fingerprint for the other, and we can tell if they're similar or not. Okay? So what we want to do is we want to function on these fingerprints, which are essentially much smaller than the file, and that gives you information on this distance between the files, the similarity between the files. So the fingerprint we suggested at the end of lecture last Tuesday, was this, we take the fingerprint scheme itself. This is the scheme, like the MD5 scheme. It's some sort of hash function. Here the scheme is determined by this random choice of pi. Okay, so we take all the words in our universe and permute them randomly. Now we have an order on all the words in the dictionary, essentially. And it's a random order. It's not alphabetical, it's random, okay? So now you say for the first word, the fingerprint is just take every word in X, figure out where it is in that permutation, and choose the word in X which is first in that permutation, okay? So it's a subset of the words in the permutation. The words in X, it's a subset of the words in the dictionary. You pick the first word in the dictionary that's also in X, okay? This pi dictionary. It takes time to process, right? Because for each word in X, you have to figure out where it is in this permutation. So it takes a while to figure out where it is, okay? But once you're done, you're done. Okay, once you've computed this fingerprint for X, that's the fingerprint. Okay, so what it allows you to do is now if you want to compare X tilde, you know X tilde now, and you want to compare it to Y for different values of Y, you don't have to recompute the value for X every time. Or if you have a bunch of files and you compute the fingerprint for all of them, then for any pair of files, you can easily estimate the distance between them, or the similarity between them. Okay, so what we showed is it's sort of very clear, and you should do this as an exercise, that the distance between these fingerprints is equal to the expected value of this distance, right? What does this correspond to when it's one word? It's just 1 or 0, right? There's, now the x tilde is a one-word file. Now y tilde is a one-word file. And the similarity between them is 1 if they're the same word and 0 otherwise, right? Now the probability that, that it's 1 just depends on how many words they have in common. Okay, so the expected value of this 0, 1 variable is exactly equal to the distance. So what we wanted to do is we wanted to figure out this distance. And what we did is gave a we gave a sampling scheme or an estimator which would compute the distance for us, or whose expected value was equal to the distance. Okay? In some sense, you could have done this another way. You could pick 2 random words in x and y and see if they're the same. Now that has a different property, but that's also another estimator. Okay? If you pick both words in the intersection, then you get 1, and otherwise not. Well, you have some probability of 1. So now, okay, so it's an estimator, right? It's an estimate. So when you have an estimate for something and you want to make it, it's not that j of x, y in this case ever gives you j of x, y, right? It's either 1 or 0. It never gives you the right value. But the average value is correct. So what you can do with an estimator is you can do it again and again, and then you can compute the average value. And what is that average value going to be? What you want. Okay? So that's all we're saying. So now I'm denoting x hat or x bar as one of these signatures, these fingerprints, except I do it k times. Okay? And so now what happens is this Descartes distance similarity between x hat and y hat sort of approaches j of xy for large k. This is just flipping coins. You're estimating the heads probability of this coin. Okay, so this is a paradigm. It's actually the paradigm in statistics, right? In probability and statistics. Okay, it's also a paradigm in algorithms. Okay, so now what we're doing is we're going to, the notion of streaming is force yourself to use very little space, and you see that before. What we want to do is take this, maybe some large amount of data, and only look and shove some information into a small amount of data, and then be able to do some computations and comparisons and calculate things. That's what we want. Okay, and what the next lecture, this lecture, and in fact last lecture, is how to estimate or come up with cool estimators using hashing. Okay, that's how they're all, there's a theme here. Okay, does that make sense? And we use it everywhere as computer scientists. These are one of your coding questions. Used to be 5 or 6 years ago. All the answers to the coding interviews were hashing. So now they're a little bit more varied. Okay. So streaming is you're given a set of elements coming to you in a stream, much like the SHHH, and you're giving them one at a time. You see them one at a time. You know, Pikachu, Squirtle, Mew, Pikachu, and so on, right? So I guess this was more relevant when Pokemon Now, is that a game? Oh, Pokemon Go, okay. Pokemon Go, okay. Okay, well, maybe that was more relevant then, but okay, you got to get them all, right? No, okay, we don't want them all. What we want to know is we're going to restrict our space. So we're going to restrict our space to something called polylog. So essentially, it's the size of the stream is n. It's very, very long. Think of it as really long. And you have some amount of space, and you're really limiting your space to a very small amount. Okay? So what you want to do is as the stream goes by, you have to forget it. You're forgetting what was in the stream. This amount of space is not enough for you to remember what's in the stream. But you want to calculate things about the stream without remembering very much about it. Okay? Okay, so you're modeling large data, but you're using small space. Okay, so the space in your algorithm is sort of this thing, this jewel, this fingerprint of the whole past that allows you to conclude something, okay, about the stream. Okay, that's the goal of this model, is to see how little information, in some sense, you can remember about the stream and still compute something interesting. Yeah. C is just some constant. Log squared, log cubed, log to the fourth. Okay, it's some constant. I mean, once you make C to be log n, then it's n again, so then you can remember the string. So C is some constant, some small constant. And our algorithms are going to be 3 or 4. Okay. The algorithms I'm going to show you will be 3 or 4. Okay? So this is an extreme mismatch, right? You see I did this visual trick with large and small. Yeah. It's an extreme mismatch. But if it was really proportional, large would be big, big wouldn't fit on the screen, and small wouldn't fit in a pixel. So, okay. So which item appears the most? Pikachu, yeah, okay, good. Well, you can't do it without little O of n space. So we're going to prove this later. So what it says is you can't actually do this. So one question about the stream is which one appears, you're going to be able, you can't remember everything about the stream. I already told you that. Okay, we're really thinking about what can you compute with very little space. Okay? So you can't remember everything about the stream. And this particular thing you can't do. You can't do this without little O of n space, with less than really remembering everything about the stream. And why is that? Okay, we'll prove an impossibility result, but the idea is you can probably guess. It's that it's some information theoretic thing where it says you really have a stream with only one of each kind of item. If you ever see one with 2, that means you know something about the stream. Like you know everything about the stream if you just ask which item appeared more than once. So, or did an item appear 0 once, one time? That's the proof. I will show you that later. Yeah. Little o means less than, asymptotically less than. It means that for all constants, your function is less than c times n. Okay? For all constants c, no matter how small c is. Yeah. N is the length of the stream. Okay? Okay, but we can approximate the item which appears the most. Okay, so that I'm just like justifying to you why I'm going to approximate. I have to. That's the answer. Okay, so now, what's a clever way to approximate? So now, first of all, a clever way to approximate is to define approximate cleverly. You want to solve a problem, you make the problem up so that you can solve it, right? This is not an unreasonable thing, but this is the way we're going to define our notion of approximate. Okay, we're going to try to get within an additive n over k. Okay, that's our goal. Okay, so we're going to try to find the maximum or the heavy hitters, anybody who you know, let's see. Let me tell you, I just want to, what I'm going to do now is I'm just going to count for each item. For each item, I want to maintain a count, and I want to say, approximate that count to within an additive n over k. That's how I'm defining it. Instead of finding the most frequent item, I just want to approximate the appearance of every item of value n over k. Now, what is the problem with that? Already there's a problem with that statement. Well, there might be n items. If I keep a count for every one, how many counts will I keep? N. So how much space does that take? Yeah, that's a disaster. Okay? Already I don't want to use n space. Okay, but I'm okay with using k space. Why might that be? Well, let's see. Can I get an accurate count for the k plus? What's an accurate count for the k plus 1 most frequent item? That's within an additive n plus k. n over k. If I add n over k, what the k plus 1 item, how frequent can it be? Can it have more than n over k items? Occurrences? No. So what's an accurate count? Is it 0? Is 0 within n over k of the k plus first most frequent item? Right? See how clever the definition is? Right? It says I don't have to remember anything about any item that's not in the top k. I know I can just output 0. So I just need to keep a table in some sense of the counts of the more frequent items. In some sense, that's what I want to do. But even then, that's not so easy either. It's like, well, how do I remember which ones are the most frequent? I mean, the most frequent at this point might change, right? It may be that one I'm not keeping track of is not in my list. And it sort of goes up and counts over the ones in my list, right? So it's still a puzzle. It's still not easy, but at least it's possible, right? The k plus first most frequent item occurs less than n over k plus 1 times, less than or equal to. So this is a terrible estimate, but a 0 estimate is fine. It's not relative, but it's not relative to the value there, right? But you can just output 0 for anybody outside of the top k items. Okay, and now let's say no item is more frequent than n over k. Maybe you have one of each. What can you output for every item? 0, right? So if there's no item that's very popular or it appears in the stream a lot, you could just output 0 always. If there's a few items that are, you just sort of need to figure out how to keep track of those, right? Okay, so how would you keep track of those, right? This is a puzzle, right? Now it's a puzzle. How do you keep track of the k most frequent items, more or less, in some sense? That's what really we're asking for. Okay, so it's only a reasonable question for the most frequent item. So here's the algorithm. We're going to have a set of counters as we expect, right? We're going to count something. But now we're going to do something completely bizarre. Okay? It's really bizarre. Okay. Oh, no, it's not so bizarre. If xi is in S, you increment xi's counter. That's not so bizarre. It's fine. If xi is in there, okay? Okay, if S has space, what you do is if xi is not in S, if it's in the set of counters, if you already maintain a counter for xi, you just increment that counter, okay? If x is not in your set of counters, S is your set of counters, if the set of counters has space, you add xi to S with value 1, because you've seen it once, okay? This is the bizarre part. If xi is not in S and S doesn't have space, you just decrease everybody's value by 1. Right? It's odd. Right? And you then, if some counter goes to 0, you just delete it. Okay. So intuitively, well, okay, maybe if some counter, if it appears a lot, you would expect to eventually, if there wasn't space, you will eventually say it appears a lot of times in a row. If there isn't much space in there, you keep decrementing because you don't have space. You're like, dude, I want space. I'm going to make you guys go to 0. And then it will make somebody go to 0, then make them have space, and then you put that item in. But it's not that clever. It doesn't know who's heavy and who's not. It doesn't know what's going to happen next. It's a very local algorithm, right? It's shockingly local. Okay? You get one, you do something. You get one, you do something. Okay, so here's the state of the stream. You can see what it is. My k here is the k counter is 3, so I'm only allowed to have k counters in my state for my algorithm. Now again, you can think of this state as the state of this algorithm. You can think of it as a condensation of the stream you've seen so far for this problem. Okay, a fingerprint of sorts for a particular problem. Okay, so the previous state was this. With 1, you put in a counter. The left-hand side is what item you're counting. The right hand, the second one in the pair is the value of the count. So you've seen 1 once. Now you've seen 2 once. Now you've seen 3 once. Now you see 1 again, and you see that what we've done is we've incremented 1 to 2. That's a local operation, right? Incremented 1 to for the number of times we've seen 2 is 2, 4. Now this is the crazy one. We see 4. We'd like to put a counter 4, 4 in our item. Maybe I should have these be A, B, C, D. But we should have a counter 4, 4 in our state. But there's no space. There's only 3. I'm only allowed to have 3 counters. So what I do now, when I see the 4, is I decrement every item. Okay? Bizarre. Okay, but that's the algorithm. Okay? So there's some intuition why it makes sense. If you see 4 a lot of times, it's going to keep decreasing. Now there's a 0 counter, and I can delete this one, and the next time I see 4, I could put 4 in. Right? If I don't see 3 again. Okay, so some intuition here. Okay, so this is the algorithm. Okay, what's the estimate for an item? If it's in the counter, it's the value of the counter. If the item is in there for any, now I'm going to ask you, how many times did you see Pikachu? Now you have a set of counters, and Pikachu is not in the set of counters. If it is in the set of counters, you just report the number. If it's not, you report 0. Okay, so this is never an overestimate, right? Because only I should have highlighted in blue both 3 and 2. If x has space, you add xi to s with count value 1, and you also increment a xi's counter when you see it. So you never get a counter whose value is larger than the number of times you've seen the item. Is that clear? So it never overestimates. Okay? You increment once when we see an item, you might decrement. So it never overestimates. Now the question is, how many decrements, how many times can we execute this line? Okay? Okay. Is it n? Is it the length of the stream? What do you think? Or is it n over k? Is it k? I'm going to tell you, but you should calculate it. This is an easy calculation. Which one is it? Who thinks it's n? Well, that's an upper bound, so everybody could raise their hand for this one. Did everybody raise their hand for this one? Everybody raise their hand, because this is true. I'm telling you this is the answer. It's never more than n, right? Okay, how about n over k? Is it never more than n over k? Okay, is it more than k? Is it never more than k? Okay, good. It's n over k. Okay, so decrement. So the point is, when you decrement the counter, you decrement how many counters? K counters. What's the total number of increments you do? So the total decrement is the number of times you did it times k, right? Because every time you subtract 1 from k different counters. So the total amount of decrease is t times k of all the counters. Now what's the total amount of increase of all the counters? How many times when do you increase a counter when you see an item? How much do you increase counters by when you increase an item, the total sum? 1. So the total increase in counters can only be n. The total decrease in counters is at least t times k. So there's n items, there's the total number of increments in both line 3a and 2 is n. The total amount of decrease is t times k. And the total amount of decrease can't be more than the increase. Okay? So that says t times k is less than n, which says that t is less than n over k. So that says your counter will never be off by more, at most, n over k. Okay? Okay. So now you want to have an intuition check, right? Now I'm confused. This proof was a little too easy. So let me just tell you that there's something kind of, when I did the proof I was going over, I was like, wait a second, I'm a little confused about the timing of all this. What if an item appears greater than n over k times? How do I know its counter is even in there? Well, the total number of times it's even in the table, if it appears more than n over k times, it has to be in the table, right? Because every time you would have added it or decremented it, and the total number of times, actually this should be a 2, can only be, every time it either had to be incremented in number 1 or it had to decrement everybody else's values. So everybody else can only, the total number of times it could be decremented is n over k, the other n over k times it must have been added. So once it's bigger than 2n over k, it's in the table. Okay, so I was just trying to understand where the intuition is in this proof. Okay, what's the space that's used? How much space are we using? Yeah, it's k times log n, because the complexity, it's just k times whatever. Log n comes from two places. You have to record the item, what the item looked like, whether it's Pikachu or whatever, maybe that's log n. What else is you have to record the count, which may be as high as n, and that needs log n bits. Okay, so it takes O of k log n bits. Okay, so now what else? Okay, what else do you want to compute? So this is cool. This is sort of the best you can do, right? You're trying to remember the k. You could have to remember k different items. So you sort of need order k space, and the log n is just a count. Okay, so it's pretty much optimal. Okay, so when you want a stream, a bunch of data, one of the things you often want to compute are moments, right? The variance and the mean and all these things, right? Okay, so they all really work out to something like this. You want to sum the number, the sum over I of mi to the k. So mi is a number of items of type I. So this is slightly confusing. You better pay attention, otherwise you're going to get completely lost. So you don't add the value of item I to the k. That's not what we're doing. We're trying to figure out, we're thinking of the stream as a histogram, okay, over the items. And we're calculating the value of mi to the k, where it's the height of the histogram to the k. Okay? So that's the distributions that we're working with. Okay, so it's the number of items of type I is mi. Okay? And so it's a number of Pikachus, a number of Squirtles, the number of Mews. Okay, so what is F0? Okay, so you take the sum over I of mi to the k. Now k is 0 now. What is mi to the 0? Yeah, so what is it telling you? The number of i's that are different. Okay? Okay, so this is, while it's a weird thing, but you're just saying, how many different things do I see in my stream? Right, which is also a natural question. So moments are nice because you come up with something that's natural. What about F1? Well, how do you compute this? I don't know. Okay, we're going to show you how to give some approximation to this. Okay, so the length of the stream, that's F1, right? Because what is mi to the 1? Yeah, and now if you add up the number of times each atom appears, what is that going to equal? Yeah, so that's pretty easy to compute. You just count the length of the stream. You just increment a counter every time you see an element, right? That's an easy one to compute. F2, how do you compute that? Again, that's also not easy. Well, I mean, I don't know. It's easy. I'm going to tell you how to do it. So I don't know. You could decide whether it's easy. Okay, so now I'm going to prove a lower bound that says you can't actually do this exactly. You can't compute the number of distinct elements without using order n space, omega of n space. It's also a lower bound for the approximating the frequent items very well. Okay, to find the max item is actually a hard problem too, if you don't have this additive n over k error. Okay, so how many distinct elements? How many distinct elements are here? Yeah, that was omega of n time, right? So clearly that's the lower bound. So it's apparently, haha. Okay, space. It's the final frontier. So you guys, that doesn't work anymore. You don't even watch Star Trek. Do they still say it's a final frontier in Star Trek? No, space is the final frontier. Algorithm takes a stream, S. This is the lower bound. When you have a lower bound, you make your algorithm do something. That's what you do. You're saying, I don't have an algorithm like this. Then you say, well, you make the algorithm do something for you that would be impossible. Okay, so that's what I'm going to do. So I'm going to take my algorithm that somehow uses less than O of n space as its space, and I'm going to feed it a stream, which is some subset of 1 to n. Okay? First of all, how many subsets? How many subsets? Oh, there's no battery. Okay. This is probably not a good sign. Open, open, close, open. Okay. I should have seen which way it went in. That one went from red to nothing. Hello? Is this one better? This is not better. All right. Okay. All right, so how many distinct elements? The answer is 3. The lower bound, that's the dumb joke. Okay, so algorithm A takes a stream and maintains a number of distinct elements. S is a subset of n. How many subsets are there of the numbers from 1 to n? 2 to the n. Okay, that's already going to be the issue. Right, how many different subsets are there? 2 to the n. So your space after this, if it needs to remember the subset, then you're done, right? If I could show you that this algorithm, now what it needs to do is be able to answer queries. What's the most frequent item? Okay, well that's not too hard. You can just pick one of the items that you saw. But now I got to engineer it so it actually can detect which subset it is. So if the algorithm has to know which subset it is, it has to use n space. Okay? So the question is what the algorithm is saying is X and S. That if I can answer this question, the algorithm itself better be able to remember things about 2 to the n different configurations, which means it better use n bits. Okay? So what we do is we take the stream of S, we keep it, we know the algorithm has some representation, which is presumably less than n bits, and then what we do is we say, oh, is X and S? Then the way I answer this question, is X and S, is I add X to the stream, I append it to the end of the stream, okay, and I make the algorithm do what it does, I don't care what it's doing, okay, and then I ask it, is X and S? And if it says yes, it would have told, or would I ask it, what's the number of distinct items? If it went up by 1, then I knew X was an S. If it did not go up by 1, I knew X is not an S. So the algorithm can be used with its internal state to answer this query. And answering this query, we know requires omega of n bits of storage. Okay? So the algorithm's internal state must know which subset you're talking about, because it doesn't know which question you're going to ask. Okay, and there's 2 to the n possibilities for S, which requires omega of n bits. Okay, so it's this information theory argument. This is where information theory works. Information theory doesn't work with computation, but it works with storage, right? We're saying you have to use a lot of storage. Okay. So now we know we have to approximate, so it's going to be an excuse for the terrible things we're doing. So the lower bound applies to the most frequent item as well, and so on. Okay, so we can't get it exactly. We can't get the number of distinct elements exactly. But let's try to get them to within a factor of 2. Say it's either less than k or more than 2k, right? We're computer scientists. We're happy with that. Okay? Sort of. So if the number of distinct, our algorithm, what it needs to do is it needs to maintain a data structure and go through the stream. At any point in time, it should answer no if the number of distinct items is less than k, and it should answer yes if the number of distinct items is bigger than 2k. And I don't care what the algorithm says in between. It can answer yes or no. We're not going to penalize it. All right? It's an approximation. Okay? So we're going to take a randomized algorithm here instead of a deterministic algorithm. So what we're going to do is choose a random hash function, h of n to b, where I guess b is k. If any h of xi is equal to 0 at the end, so we process it, we keep hashing all the items, right? And what can we do when we hash them? We could just record in that hash bucket. Well, now we have a bucket of size, a table of size k. And for each one, if we ever see an item that hashes to that bucket, we just mark it as not empty. Okay? Something landed in it. If it's empty, now at the end of the algorithm, after we process the end streams, we say, if the first bin is empty, we answer no. There weren't very many items. If the first bin is full, we answer yes. Oh, the no and yes are slipped. Okay, the no and yes are slipped. Okay, so yeah. Okay, so what you say at the end is if the first bin is empty. Oh, okay. Oh, I see the way it's phrased. I apologize. I misunderstood how it's phrased. If at any point during the algorithm, one of the items assigns itself to this first bin, you just answer yes forever. Okay? That's what this is saying. Okay? If the hash of an item is 0, then you answer yes. Otherwise, you answer no. Okay, at the end of the algorithm. You keep answering no until you get a first yes, and then you keep answering yes. Okay. Okay, so what's the probability that the algorithm, the output is no, if the number of distinct items is less than k? Okay, so what has to happen is every single time for this, every different item, this big N, the number of different items, if I see an item and I see the item again, where does it hash? Where's the second time? Where does it hash the second time? Same place, right? So I'm not raising this to the power of little n. It's got nothing to do with the size of the stream. So I'm saying that if it answers no, this item was not mapped to the first bin. So not means this is the probability it was mapped to the first bin, which is the 0th bin, and 1 minus that is the probability it was not mapped to the first bin. So every single time for every single distinct item, they need to be mapped, not mapped to the first bin. So this has to happen, and this has to happen, and this has to happen n times, big N times. So you take the product. Okay, so you get that, and here it's the other way around. This is the expression if it's bigger than k. It's the same expression here, but we get a less than 2 to the k here. Because we know this is at least, n is at least, n is at most k, so this is bigger than this value, because every time you multiply by one of these numbers, it gets smaller. And this one, if n is at least 2k, every time you multiply it here, it gets smaller, so this is bigger. Okay? Okay, what are those expressions? We're taking k to be b. So if you take k to be b, what is 1 minus 1 over b to the 1 over k to the k? It's e. It's 1 over e. Okay. So in the limit, this is just an approximation for e, or 1 over e, and this is an approximation for 1 over e squared. Okay. So now this algorithm does really, these two cases correspond to two separate situations. In one situation, it's like a coin, where the heads probability is the heads probability is 1 over e. Okay? And in the second is at least 1 over e. And the second case is where the heads probability is at most 1 over e squared. Okay, so now the problem is just distinguishing these two coins. And what would you do to distinguish two coins? Which coin it is? I have a coin. I tell you it's either 3/4 biased or 1/4 biased. What would you do to tell me? You just keep flipping it, right? You flip it until it converges to either 3/4 average or 1/4 average. Okay, so many trials here. You can't do this algorithm again because you would have to go over the stream many times. So what we do is we do it in parallel. We just run many of these things, many of these algorithms in parallel with different hash functions. Okay, does that make sense? Okay. Oh wow. Okay, that's the law of large numbers. Okay. So the problem with this analysis is the number of bits for a random hash function. Okay, so a random hash function is sort of like throwing each item into each of the n items into one of these k bins. So that's the amount of space to actually specify it is, there's k times k times k is a number of hash functions, right? There's k possibilities for each item. So the number of bits is too large. So you can't just use a random hash function. But we have a solution here. We have these universal hash functions that we talked about last time. And what we said is that instead of just taking a hash function that throws things in at random, we're going to use one of these linear congruential hash functions where we pick these A and Bs. And we have these properties. H is a family of hash functions with range R. All the hash functions map items into range 1 to R. And now it's universal. What we said last time, the family is universal if by selecting a random hash function from this family, I get that and that's what the probability is over that sample space. The probability over these functions, these H's, of H of A equaling H of B is equal to 1 over R for all A and B. Now, pairwise independent, this is another version of what it means to look like random. It says the probability that H of A is mapped to any R and H of B is mapped to any S is 1 over R squared. Okay? So it's as if they were random, right? The probability that H of A goes, that if it was a random hash function, the probability that A gets mapped to R is 1 over big R, and the probability that B is mapped to S is 1 over big R. So it's a product. Okay, and if it's T-wise independent, it's the same thing. You're just doing it for T different values here. Okay? So it really looks completely random with respect to sets of size 2. It looks completely random with sets of size T. Okay, and we saw an example. This is a T-wise independent hash function where you pick the coefficients of this polynomial. You remember polynomials from 70? Yeah. Okay, so this is one of the, again, polynomials that have very nice properties, right? Now, you could also see that it fails. This is a T-wise independent hash function. If I told you the value, this is just saying what are T points on the thing. This is basically polynomial interpolation. It says for any T points, I could find a hash function that hits those T points. Okay, so that's what it's saying. Now, if I try to do it with T plus 1, I would completely know the polynomial, so I would not have this independence. So it really is limited to T-wise independence. the last time we proved 2 wise independence for this in the proof of universality for this hash function. Okay, so now, so this is the algorithm that we did before with the random hash function. So now what we're going to do is, the toy problem is the k and the 2k problem. So what we're going to do is now this hash function is not so nice. We did this thing here. We said 1 minus 1 over b to the k. Now that's using independence to say that you can multiply these things together. Okay? We used independence here. And that's fine if we only use 2. If we did 1 minus 1 over b times 1 over 1 minus b, that would be fine. But it's not, you can't do this calculation if these things aren't independent. Okay? So what we have to do is bound this probability of a of x equaling no in the context of a hash function that's 2 universal. Okay, so meaning we can only argue about 2 values at a time and the independent and the probability of those. Okay, so we're going to remember the union bound, the probability of an event A and the union event B is less than or equal to the probability of A plus the probability of B. And this is also the union bound if the probability of a bunch of unions is the sum of ORs. ORs, union is also OR. So the probability of yes, that if n is less than k, is a sum over all the items of the probability of that item being 0. Okay? Is at most that sum. Okay? So that's what the probability that the algorithm answers yes. And that's less than, there's k different items, and the probability that each one of them is less than, is equal to 0 is 1 over 4k. Okay, so that says the probability of the algorithm saying yes with 2 universal hash functions is at most 1/4. Okay? And now there's a slightly more complicated inclusion-exclusion. So that's a way to get an upper bound on unions, right, is the union bound. The way to get a lower bound on unions is to use the first step of inclusion-exclusion. And inclusion-exclusion says it's the probability of A plus the probability of B minus the probability of A intersect B. Okay? It says it's greater than or equal to. It's actually equal to for 2 items. But this is where it becomes interesting. It's greater than or equal to this term. Okay? So the probability of the union of all these events is at least the sum of all the events minus the intersections of all the pairwise events. Okay? The figure, if you really want to think back to the thing, is if you take 3 events, what we're doing is we're adding up the areas of the 3 circles, and then we're subtracting the intersection in the middle. And what we've done is we subtracted the 3-way intersections too many times, and that's why it's a lower bound. Okay? Okay, so now the probability of yes, given that n is greater than or equal to k, is 2k is 2k over b, which is just plugging in 2k times 1 over 4k there. And then minus the intersection of the events. And those are, now here's where we're using 2 universal. Here we're talking about the probability that both of them equal 0. Okay? And so that's, there's k times 2k minus 1 over 2b, which is, this should be over b squared. Sorry. Okay. And then I'll fix that. Okay, which is 3k, which is 3/8. It's b over b squared, right? Each guy is, every one of them is 0 with probability 1 over b. So 1 over b times 1 over b is 1 over b squared. Okay, so now we have 2 coins again, 1/4 and 3/8. One is heads with probability less than 1/4. One is heads with probability greater than 3/8. So it's a gap of 1/8. We can flip the coins many, many times in parallel. Okay? Okay, sounds good. Okay, to pump up the volume, or to pump up the probability, right? That's what we do. Okay, okay, so let me give you a quick break. Yeah, a quick break, yeah. I'll give you a quick break. Yeah.
So what's the purpose of finding out the gap between the two? Like once you have the gap, what's the significance?
What is the significance? Yeah.
Yeah.
Yeah, what is the significance? Yeah, what is the significance?
Oh, I'm not really sure.
What does the algorithm do? What does the algorithm do?
Oh, the algorithm finds a number of, find a distinct element.
It either answers yes or no.
Yeah.
So what are the two different things? When does it, okay, just what's the probability it answers yes?
Oh, the one that you had previously is 1 over, 1 minus, I think 1 over.
No, no, it depends on the situation, right? We're trying to distinguish two situations. What are the two situations?
Where one is smaller than k and one is bigger than 2k.
Yeah. So it answers yes with different probabilities in those two cases, right?
Yeah.
Isn't that what you want? Do you want them to answer yes with the same probability in both cases?
No. So there should be a gap between the two probabilities.
Yeah.
Okay, so what if it's between k and 2k?
We don't care.
Oh, so are you going to elaborate more on what?
Well, we're only trying to get a 2 approximation.
Okay, so what's the significance of, like, k's just seems very arbitrary, so how do you pick the k?
Well, yeah, we'll talk about that a little bit, but it's a toy problem right now, right? We're just saying, is it k or 2, less than k or bigger than 2k? And so how might you, how would you deal with all k?
Yeah, I'm not sure.
Well, how would you do it? Think about it.
All right, so if I want to do with all k's, then I'll just try for every single possible k from 1 to 10.
Right. You can do that. Okay, what else could you do?
I could do binary search.
Yeah, you can do all powers of 2 for k's.
Oh, okay, and then you get an approximation to the number of distinct values.
Right.
Okay, I get it.
All right.
Yeah, and how does it relate to the coin stuff?
What is a coin?
Oh, yes or no?
Yeah.
Oh, okay. Yeah, so that's why it's a coin.
Yeah.
Okay, I understand that.
Okay.
Yeah, thank you.
Yeah, because the coin is different. You get a coin in the case you're bigger than 2k, and you get a different coin in the case you get less than.
But different coins. I thought you meant different sides.
No, different heads probability.
Okay.
Right.
Yeah, so different coins.
You get a different kind of coin, right?
Oh, okay. One with 1/4 probability, one with 3/8 probability. Okay. Yeah, thanks for clarifying.
Yeah.
Okay.
Yeah. No, it's a good question.
All right.
The reason I'm asking you questions is it's just better that way.
Yeah, I understand.
Yeah.
It also checks my understanding.
Right.
And makes sure.
Yeah. I mean, because if I talk, it's hard to follow. Yeah, for you. Yeah.
Okay, that was helpful.
Yeah.
Explaining again why h of x equals 0 is the case for yes instead of I kind of thought of it.
Okay, if there's a lot of elements, then you're going to hit 0 more often.
Like for any
2k. If you have 2k elements, are you more likely to have one of the elements hashed to 0 than if you had no one element?
Sure.
Yeah. So it's yes means more than 2k. No means less than k. So yes means if you see it, if one of your elements hashes to 0, you say yes.
Also, just a clarification notification. So for the hash, does it mean that I want to map from all values of n to less than 2 or 4k?
Here, just a second. Yeah. For all the values, you hash that element and see if it's 0. Elements in the stream. Yeah. 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 Okay. Okay, so let's just do a quick. Okay, let's do a quick review. What we're saying is if there's more than 4k items here, more than 2k items that are distinct, we're going to answer yes with probability 3/8. Okay, that's what this algorithm will do, even with this 2 independent hash function. Okay? And the reason I did this different analysis is here I only thought about 2 items at a time. 2 items mapping to the same place. Okay, that's why I was able to get away with 2 independent hash functions. Okay, but here in this case, if I have a lot of different items in the stream, I'm very likely to have one, or very likely, meaning at least with 3/8 probability, one of them mapped to 0 out of these 4K elements. And the first case says, if I don't have very many different items in the stream, say I had no items in the stream, nobody would be mapped to the 0 in the buckets, right? So I have not a very high probability of mapping anybody to 0. So now all I want to do is say which one of these 2 cases am I in? Okay, whether I'm bigger than 2K or less than K. Okay, because that's sort of a natural problem. I mean, obviously, which case should I choose? I'll go on and deal with all that. But this already as a black box is interesting. It says if I'm very small, I'm very unlikely to map an item to 0. If I'm very big, I'm very likely to map an item to 0. Okay, very is all relative, 3/8 versus 1/4. Okay? Okay, so and then now we have this turnoff bound, which is just says, now we're just, what we do is we're given a coin, essentially. And we're just asking whether it's this kind of coin, the one that comes up heads with probability more than 3/8, or the first kind of coin, one that comes up with heads less than 1/4. Okay? So all we do is we keep flipping the coin. So for streaming, what that means is running many copies of this algorithm. Okay? In parallel. You just use a different hash function, you run this algorithm in parallel many times. And then you have the coins compute the point. And that's what we're doing here. So many copies, each full run of this algorithm is one coin flip. So you run many flips of this algorithm in parallel, and then you can apply a turnoff bound. Okay? So, but what it says is if you run theta of log of 1 over delta independent copies of the algorithm, you'll output yes if more than 5/16, which is just the halfway point, and you output no otherwise. Okay, so we can just plug in epsilon. This is just a calculation. If you plug in epsilon equals 1/3 into the theorem, then you can get some bounds on what you're doing. Okay. Okay, so now that tells you, if I tell you the K, you can tell me whether it's bigger than 2K or less than K. What you want to do is know which K is it. Okay? So what you do is you try a lot of different values of K. Do you try every value of K from 1 to n? No. Because if you did that, that would take you along, then you'd have a lot of data structures for every value of K. But what values of K should you try it for? Yeah, you can choose, you can do this whole thing instead of K and 2 times K. You could do this whole thing and do all this analysis with K less than K and bigger than 1 plus 1 or epsilon K. Okay? So you can redo it this way. And then finally, you can pump up the probability. In this case, you could use a different value of K again. And now this final thing, the one I just explained, is you can think of changing the values of K. I could run this algorithm for this interval when I'm thinking of 2 instead of 1 plus epsilon, and this interval, and 4 to 8, and so on. How many of these intervals are there? Log n. Now if I replace the 2 with instead of 1 to 2, I did 1 to 1 plus epsilon, and a 1 plus epsilon to 1 plus epsilon squared. How many intervals would this be? It's just a log of base 1 plus epsilon to n. Okay? So now what that tells me is I can put all this parallel stuff together and get this much space. Okay? So this is this log to the c, where it's log cubed. Okay? So you can run all these things in parallel. Now this seems terrible, but it's still way better than n. And in real, they use this all over. It's used everywhere, and by these big companies like Google and Amazon and, you know, where I used to work, Akamai, they use this stuff a lot. Okay. Okay. So now finally, okay. So let's go on to another application. How do you do the second moment? And this is another cool trick. It's like cool tricks after cool tricks, right? Like here we could do this toy problem, and then there's all this other stuff where you just throw on. But the toy problem is very simple. K versus 2K. Is there very few items or a lot of items? And you just hash them into a bucket, and you're just seeing if the first bucket is empty. If there's a lot of items, the first bucket is not very likely to be empty. If there's not very many items, the first bucket should be empty. That was the idea. Okay? So this one is going to, now we're going to try to compute the sum of mj squared. Okay, so the core algorithm is going to have a cool trick again. Right? The cool trick there was hashed a bucket of size, hashed a table of size approximately the number of items you're thinking about. Okay? That was the trick before. What's the trick here? Okay, so you know, squares are hard to understand for students and me. So let me just tell you the trick here. So the random h from a four-wise independent family, just think of it as a hash function. And this hash function, it's very, very simple. It either maps everything to +1 or -1. Okay? So for each item, it assigns it either +1 or -1. Okay, so and then you output z squared, which is the sum of I of h of xi squared. Okay? Now that's not exactly the sum of j mj squared, right? It's not at all it. Now we're taking all the items. That's summing over the items. So F2 is summing over the items in the first line. In this step 2 of the core algorithm, now I'm summing over the elements of the stream. Okay, the elements of the stream are different items each time. So now I'm taking the hashes of those. For each element in the stream, we're assigning it plus or minus 1. So this is really just summing a bunch of plus and minus 1s up in the middle, inside of the step 2. Okay, and then squaring it. You're just adding a plus and minus 1 and then squaring it, right? Odd, bizarre, right? That's all you're doing. And somehow that's going to be related to mj squared. Okay? It's a little shocking. Like, how could that possibly be? Okay, so this is a random variable. Why I call it z squared is z is a thing inside. It's the sum of the I of hxi. That's the sum of a bunch of random variables, plus minus 1 random variables. Okay? And what we're going to show is that actually the expectation of z squared is exactly our frequency moment. Okay, so h of j is, you think of h of j as yj, so it looks like a random variable that you saw in 70, right? Or stat 134, whatever probability you took. Okay, so hello, did it turn it off? Okay, good. Okay, so z is equal to the sum of these things, which is, okay, now you can get the mj's out. So it's the sum of these hf of x, h of xi's. And this is where we're using the hash function. We're not flipping a coin for each item in the stream. We're flipping a coin for each item. And when we see that item again, we use the same value. So the first time we flipped a coin for Pikachu, and it said +1. The next time we see Pikachu, we add in +1 again, right? Because it's a hash function. It's a function of Pikachu. Okay? So when you see it that way, this is just counting, in some sense. It's a sum over j of yj times mj, right? Because yj is either +1 or -1 for all the items. So you could write it this way. Okay? Okay, now when you square it, it's like, oh no, you're going to get this stuff. Oh no. Oh God. Okay, so, okay, now you take a deep breath. The first thing is exactly what we want. And it's really exactly what we want. What's the sum of +1? What is +1 squared? What is minus 1 squared? So what's the expectation of yj squared? It's either plus 1 or minus 1. What is it? All right, that's awesome. Okay, now this one over here, these are pairwise independent. Okay, if they're pairwise independent, we could just multiply their expectations. What is the expectation of yi? And yj? What is this next thing? Right. Like, this is cool tricks, right? This is what this streaming is about. Cool tricks, right? Really cool tricks with hashing. Like, holy moly. Here's this estimator. The expectation of it is exactly what we want. Who would have thought? Right? Okay, so now what do we do to show good probability of success? That's the expectation. Now again, we could repeat with coins or blah, 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 but that we do it a slightly different way here, which is instructive. So let me show you how to do it. What we're going to do is you're going to use Chebyshev. Okay, we're going to use Chebyshev or bounds like that. Okay, and so what we need to compute when we use Chebyshev is we need to compute the variance of our variable. Okay, so before the variance was very easy because it was a coin. Here it's a number. We're getting out a number. So now it's not a coin, right? It's just not p times 1 minus p. It's something more complicated. So let's calculate a bound on the variance. Okay. So remember, the variance is for any random variable z is expectation of z squared minus expectation of z. I should have used x here, but the expectation of z. So what you need to compute is for your random variable, the expectation of the random variable squared. The random variable here that we care about is z squared. So we need to compute the expectation of that squared. I had x here, but I changed it to z, and now I'm sad. So, okay, but it's expectation of z to the 4th, because we're trying to predict the variance of expectation of z squared. Oh no. Okay, so when you take z to the, z squared was bad enough, right? When you take z to be this big sum and you take it to the squared power, you get all the cross terms. When you take it to the 4th power, you get a lot of cross terms, right? You get cubes and ones and blah, blah, blah. But but there's no cubes here. Why not? Why aren't anything cubes? Yeah, what's expectation of yi cubed? 0, right? So all those terms, anything with a multiple of an odd power is gone. So then now we have this expectation. The expectation of yi to the 4th is 1. The expectation of yj squared, these are 1, right? Because these are squares now. Okay, so you get this. The odd degree terms disappear in this crazy 4th power. So the variance of z to the 4th, the variance of z squared is the expectation of z to the 4th minus expectation of z squared squared, which you can check is 2 times. Yeah, you have to do some work here, but when you square this thing, you get these 4th powers, and then you get the cross terms once. Okay, so that's what happens. Okay, so when you subtract them, you get this bound. Okay, so now this is nice because this is less than 2 times f2 squared, right? Because this is just the cross terms times 2. Okay. All right, so that's good. So now we can plug it into Chebyshev's bound. We have the variance of z squared is this, and we go on. It's less than 2f2, as we said before. Now, is this estimator, right? I said we have an estimator. We go through the stream, we compute this hash function where we make everything plus minus 1, and we add this number. It's one number, no space at all, right? So is it close to the expectation? Okay, so what we want to do is, this is what Chebyshev's is. We want to say that the probability, what is this event? We want this event to be true. So the event is false. If you're far away from the expectation, this is what Chebyshev gives you. It says you're far away, farther than delta away from the expectation with probability the variance of the random variable over delta squared. For z squared, I'm just plugging in the various things in the formula. I get, I'm trying to get an epsilon approximation within an additive error of epsilon. And I get this, the probability is less than 2 over epsilon squared, and I'm sad. Why am I sad? I'm saying the probability of something bad happening is less than 2 over epsilon squared. Like plug in a half there. What do you get on the right-hand side? You get 2. You get the probability of this bad thing happening is less than 2. Is that interesting? No. Yeah, it's bigger than 1. You know, upper bounds on probabilities that are bigger than 1 are not interesting, right? Does that make sense? But we do the obvious thing. We just run the core algorithm k times once again, and then we output the average of these things. Again, the law of large numbers is equal to f of 2. The average of these random variables with the same average is the same average. We get that the variance is c squared times the variance. I'm doing the confidence interval development in 70. We're just using linearity of expectation. We get that the variance of this estimator, which is the sum of a bunch of random variables, is the sum of the random variables, independent, and so on. And now by plugging this thing in and Chebyshev, then we get that that's good enough. We can get that the probability for any delta we want failure probability. We want this to be less than 1, remember, right? The failure probability. For anyone, we can use this many. So each one of these trials is only computing 1 number. So we only need to compute k numbers, where k is this big. Okay? You can do better using a central limit theorem. A central limit theorem is turn off yeah, it's turn off.